All right. Hello, everyone. Welcome to PaleoPark Seminar. This week, we have Katie Jamson from the University of Victoria, Canada. We'll wait around for a minute or so to let people trickle in. Um, but first, we have a couple of announcements. So if you are new, welcome. The format for today's seminar will be we will have welcome and announcements for about 5 minutes. Then we will have the talk, and then we'll do moderated Q&A questions. If you have a question, feel free to put it in the chat. Send it to Nina at questions@paleoperks, um, and we will read it out for you at the Q&A portion. And then afterwards, please stick around for tea time, which is more informal discussion, not recorded, with the speaker. All right. Um, PaleoPerks values participation of everybody interested in paleosciences. Please remember to abide by our code of conduct, which you signed during today's seminar, and please mute yourself for the duration of the talk. And again, you can ask questions by chatting to questions@paleoperks host or using the raise hand function after the talk. We have closed captions, and if you or somebody you know is an outstanding early career researcher and you'd like to hear them give a PaleoPerks talk, please nominate them here. We are also looking for committee members to help organize the seminar. So if you or somebody you know would like to do that, please get in contact with us. Okay. I believe that's all the housekeeping. So I would like to introduce Katie Jamson. She did her master's in paleobiology at the University of Bristol, and is finishing up her PhD at the School of Earth and Ocean Sciences in University of Victoria, Canada. Um, she's also associated with Ocean Networks Canada. Um, all right, I guess take it away, Katie.
Okay, excellent. Well, hello everyone. Thank you so much for attending my talk today, and thank you so much for PaleoPerks for inviting me to present. It is currently 8 a.m. my time, so I apologize in advance if my brain isn't quite into gear yet. Hopefully my tea will kick in a bit soon. But my name is Katie Jamson. I'm coming scarily close to the end of my PhD at the University of Victoria in beautiful British Columbia in Canada. And on that note, I think it's important to start this presentation today by recognizing and respecting that I'm calling in from the unceded territories of Lekwungen speaking peoples, which is the Songhees and Esquimalt nations, whose relationships with these lands and waters continue to this day. Being in a field focusing on paleoceanography and paleontology in general, we inherently study deep time through records of the earth and oceans. And so it's vital to recognize that the sediments, shorelines, and marine environments we analyze are inseparable from the histories, oral traditions, and ongoing stewardship of the indigenous peoples who have cared for these lands and waters for thousands of years. So with that global and historical perspective in mind, I'd like to introduce you to the first chapter of my PhD. That is, fingers crossed, very close to publication, titled Investigating the Responses of Deep Sea Sediments to Cenozoic Paleoclimate and Paleoceanographic Events. I've been working on this project for quite some time now, alongside my supervisor, Andy Frass, as well as all of these wonderful people, Jocelyn, Leah, Shannon, Andrew, and John. So let's get going. Okay, so before I dive into my project, I wanted to introduce you to the context of my research. All the data that I work with is the result of scientific ocean drilling. And scientific ocean drilling is the process of drilling cores of sediment from below the seafloor and then bringing them back up to the surface to analyze. And this is achieved using ships like these two here. So we've got the JOIDES resolution on the top right and is also demonstrated in the video here. And then we also have the CHICU. And they're both equipped with super sophisticated drilling tools and onboard science facilities with the ability to deploy almost 6 miles worth of drill string and has ice strengthened hulls, meaning it can conduct drilling expeditions in pretty extreme environments. And over the past 50 plus years, scientific ocean drilling has recovered more than, I think it's like 490 kilometers of cores or something at this point, that has led to an insane amount of research, yielding insight into first order questions about how our planet works. So this here is a map of all of the scientific ocean drilling sites that have been explored over the past 50 years. This volume of data and advancements of scientific ocean drilling has led to some truly revolutionary scientific discoveries in earth and ocean sciences. So this includes paleomagnetism, the unifying theory of plate tectonics, their movements due to mantle convection, as well as the development of astronomical geochronology. And that's just naming a few of them. And this has enabled us to reconstruct global climate and ocean history over millions of years. So this is what sediment cores look like when they are extracted and brought shipboard to be analysed. These sediments can be analysed to look at their composition, to look at different minerals and any organic matter present, their physical properties such as grain size, porosity, colour, to give indications as to the energy of the environment they were deposited in. We can also look at sediment compaction and changes in oxygen through time. And we can look at their chemical composition and stable isotopes to give insights into paleotemperatures and ice volume. And we can look at pore water chemistry, which can tell us about post-depositional processes. But the aspect that I am most interested in is the presence of microfossils and biogenic components. And we can use these guys to look at so many different aspects of past environments, including temperature, salinity, nutrient levels, ocean productivity, availability of dissolved carbon in the ocean, like a whole heap of things. So there are 4 main groups of microfossils that are preserved in sediment cores that I'm interested in. So we have planktic foraminifera, calcareous nanoplankton, radiolarians, and diatoms. Both planktic foraminifera and calcareous nanofossils have shells that are made out of calcium carbonate, while radiolarian skeletons and diatom frustules are made out of silica. Both calcareous nanos and diatoms are single-celled algae that are typically autotrophs, and so they're found in the photic zone where they can photosynthesize. And they're both really small and mostly require microscopes to see them in sediment samples. While planktic forams and radiolarians are heterotrophs, and so they are single-cell protists, and they can span larger depth ranges in the ocean, but they're typically situated above the thermocline. And planktics and radiolarians are bigger, more like sand size, and so you can see them without a microscope a lot of the time, but we obviously use a microscope to look at their features and identify species, etc. All of these guys are so abundant in the ocean, and they provide the most continuous and comprehensive fossil record that we have, spanning back as far as the Jurassic, so roughly 150 million years ago. And these microorganisms significantly contribute to sediment composition, especially in deep sea environments where their remains form a substantial part of the sediment layers. So when they die, their hard parts made from silica or calcium carbonate sink to the seafloor. And over time, these accumulate, forming sediments called biogenic ooze. And so this is highlighted by the red box in this figure. And sediments act as a natural archive, recording details about past climate and ocean conditions. So in the last decade, we have gained a somewhat decent understanding of our modern sediment distribution, like this wonderful map from Dutkovich. However, as we move back in time, this understanding of sediment distribution and the implications this has for ocean biogeochemical cycles becomes increasingly limited and uncertain. So biogeochemical cycles are influenced directly by shifts in climate and tectonic deformation, and this subsequently influences the global sediment distribution. Now, I don't want to get too much into the chemistry here because I just don't want to overwhelm people with that. But if you remember, foraminifera and nanoplankton are made of calcium carbonate, and radiolarians and diatoms are made of silica. So when these biogeochemical cycles fluctuate, they alter ocean acidity, temperature, nutrient zones, and this fundamentally changes the global rules of deposition, so dictating exactly where sediment is allowed to accumulate and where it is absent from the rock record. So the marine carbonate cycle involves carbon dioxide from the atmosphere dissolving into the ocean, and then microorganisms like forams and nanos use it to build their shells. Then when they die, their shells sink to form sediments and rocks, and they store this carbon in the deep ocean. However, this deposition on the seafloor can't occur everywhere because carbonate deposition is dependent on something called the carbonate compensation depth, or CCD. And this is the ocean depth where the rate of calcium carbonate shells falling from the surface equals the rate at which they dissolve. So above this depth, shells can pile up on the seafloor and form sediments. And below this, corrosive deep waters dissolve calcium carbonate faster than it can accumulate. So no sediment can form below there. And so the CCD today is around 4,500 meters in the Pacific and roughly 5,500 meters in the Atlantic. But this has changed through time. And the silica cycle, on the other hand, despite this figure actually looking more complicated than the carbonate cycle, trust me, there's a lot missing from the carbonate cycle in that figure. It's a slightly easier cycle to understand, the silica cycle. So rivers transport land-eroded silica into the ocean, where siliceous organisms like diatoms and radiolarians harvest it to build their skeletons. But because seawater is naturally undersaturated in silica, roughly 96%, I think, of these skeletons dissolve as they sink, recycling these dissolved nutrients back to the surface ocean via upwelling. And so this means that only about 4% of siliceous organisms are preserved on the seafloor. And throughout the Cenozoic era, evolving climate patterns and tectonic events continuously shifted both the depth of the CCD and the strength of upwelling, which dynamically alters where and how abundantly these biogenic sediments accumulate over time. So I mentioned the Cenozoic. This study focuses on the whole of the Cenozoic era, which represents the last 65 million years since the end Cretaceous extinction event that killed off the non-avian dinosaurs. So through the Cenozoic, there is a long-term cooling trend here, and this is punctuated by various events. So these events cause changes in both average global surface temperatures and PCO2, as you can see from this figure. And just grab my laser pointer. So the x-axis here is time, which is not evenly spaced, as you can see, as we get towards the present day. And the y-axis here is PCO2, and this is average global surface temperature. And so following the end Cretaceous extinction, we see that we're in this really warm period called the warm house. And then we get into the hot house around here, which is called the Paleocene-Eocene thermal maximum, which was a rapid pulse of greenhouse gases, which triggered a sudden global temperature rise of around 8 degrees Celsius. And then as we continue through the Eocene, we see this gradual decline in average surface temperatures. And then once we get to the Eocene at Oligocene, we see this rapid drop here, and we enter into this cool house period. And this was a period of real rapid cooling as permanent ice sheets first nucleated and expanded on Antarctica, responding to the opening of ocean gateways. And then as we're moving into the Miocene, we have the mid-Miocene climatic optimum at around 16 to 15 million years ago, which was a brief intermediate warming period before the onset of the Quaternary glaciation at around 2.6 million years ago, where major northern hemisphere continental ice sheets emerged and contributed to these glacial and interglacial cycles through the Pleistocene. And then as you go through here, you can see that we start getting into future predictions. So these are concentration pathways predicted by the IPCC. And so, as you can see in this really terrifying worst case scenario event, RCP 8.5, um, basically the temperature can get up to as almost as much as the PETM over here. So quite disturbing, but we'll move on from that. Uh, these changes in temperature and PCO2 have had an impact on the CCD that people like Campbell, Palicki, Dalvand have tried to pull out of the geological record. And so, as you can see in this top figure, we have the equatorial Pacific, and then this panel on the right is the eastern North Pacific and the western North Pacific. And then this is just a general all-round trend of the Pacific, like a synthesis figure together. And so not only does this show that there is uncertainty surrounding these reconstructions of the CCD, but it also highlights that even in the same ocean basin of the Pacific, we have significant differences in the depth of the CCD. So this is kind of where my motivation comes in. And we know that the deposition of biogenic sediments is not static, but we don't know when, why, or how much these sediments have changed. And most importantly, we don't know where and on what scale they have changed. So I am inherently a geographer, and so all I want to do is make pretty maps and compare things on a global spatial scale. So we know these events occurred, but just how global were they? How do they impact the ocean's productivity, upwelling, ocean circulation, water temperatures, all sorts of things. And so we also don't know if these events impacted our individual microfossil groups in the same way either. So there have been several studies on deep sea sediment distributions and the response of sediments to Cenozoic climate transitions. However, there are very few studies that specifically look at visualizing sedimentation patterns and investigating how and why they have changed. And this is one of the only studies I've found by Bridget Wade, who looks at these sediment distributions in a visual way, but confined to key climate transitions. So we have the Paleocene, Eocene thermal maximum and the Eocene Oligocene transition. And in these maps, let's see if still got my marker. In these maps, the brown represents pelagic clays, and then the light blue up here is carbonate ooze, and then the greens represent different types of silicious ooze. And so you can see here that during the hot house of the PETM, the CCD rose, and so there are very little carbonate points, just only a few isolated areas here. But when you move into the Eocene Oligocene, there's a big drop in the CCD as we get into that global cooling. And so we can see a lot more carbonates being deposited, and then this is diatomaceous ooze, and this is radiolarian ooze coming about here. And this is likely due to the changes in upwelling regimes that mean we can still meaning that we can see silicious sediments creep in. And typically in the field of micropaleontology research, it's often confined to a through time approach and ignores the concept of space. So this means that both regional and local signals can be completely missed, that can further then be compounded when there are over and undersampled regions that can create latitudinal or basinal biases on existing temporal trends. So what we tried to do was build on what Bridget Wade and others have done, and we wanted to use as much scientific ocean drilling data as possible to get the most comprehensive look at how sedimentation has changed through time. Scientific ocean drilling has produced vast quantities of data, as you can imagine, for uses in numerous fields, and so we thought, wouldn't it be awesome if we could just use all of this data collected over the last 50 plus years and have it all in one place? And so this is where the EODP, or Extending Ocean Drilling Pursuits project, comes into play, which is a project aiming to improve the use and reuse of scientific ocean drilling data. So the EODP project facilitates the curation, access, analysis, refinement, and visualization of comprehensive and integrated marine fossil and stratigraphic data sets from scientific ocean drilling expeditions. And it's doing this by adapting two existing databases, the PBDB and MacroStrat. And So I'm sure many of you are aware that the PBDB stores paleontological records with the capability to deal with the ever-changing and evolving taxonomic concepts of fossils identified during scientific ocean drilling, while MacroStrat is a stratigraphy database that stores ages, sediment thicknesses, and lithologies in easily accessible formats. And so, like I say, anyone that is familiar with scientific ocean drilling and the different formats the data is stored in and different repositories that there are will know that this is no small feat in getting all of this together. So essentially, the practicality of using this data is really quite limited in current scientific ocean drilling databases. The stratigraphic data are stored in unconnected to each other. They're really poorly organized, hard to analyze in an effective and efficient manner due to these different repositories being formatted in different ways. And so these speech bubbles are just examples of some of the many headers that were stored in just one scientific ocean drilling online repository, which are storing basically all of the same information, same type of information functionally, but they were classified as unique headers. So anyone that knows anything about coding or programming will know that no matter how good your computer or processor is, it is never going to recognize that these headings are the same thing. So this is making data really hard to analyze without manually going through all of the repository data. But don't worry, I know you're getting worried for a second, but we did it. It was a lot of work from a lot of people, many of which aren't pictured here, but these are the people who I worked with directly and have personally helped me with this project. I can't express how big of an undertaking this was, and in spite of that, we managed to get all of this data in one accessible place to make this research possible. And with that said, let's see what I did. So overall, this study visualizes the sedimentological data collated by the EODP project, allowing for the generation of reproducible seafloor sediment maps through the Cenozoic. And this study produces maps of biogenic sedimentation in clays to visualize the spatial distribution and thicknesses of sediments from the Paleocene to the Quaternary to infer how and why sedimentation patterns developed through time and across space. So we present 3 case studies focusing on the Pacific Ocean, the equatorial Pacific, Northwest Pacific, and Southwest Pacific, providing in-depth interpretations of ocean circulation patterns and sediment changes through the Cenozoic. However, all of the maps that I've made are of all of the ocean basins, so further interpretation could be made later in other regions, not just the Pacific. So to do this, I've downloaded data from the MacroStrat API using 4 different lithology categories in the MacroStrat database, which led to me having over 90,000 lithological units, which are basically individual sections of a certain sediment type with a column, which is essentially the different cored holes. And then we have over 1,700 core holes at 639 scientific ocean drilling sites. So a whole lot of data. And the data downloads age, lithology type, sediment thicknesses, and modern latitude and longitude coordinates for each sediment unit. So to be comparable with previous studies, these lithological units were categorized into 6 main sediment types based on their primary lithology, following the methodology of Wade et al. In 2020. So these are carbonate, silicious, clay, glacier-marine, siliciclastic, and volcanic sediments. So I wanted to visualize this data to see was and if any interesting patterns could be pulled out of it. So to do this, I reconstructed the modern latitude and longitude coordinates to their rotated paleo positions from the Paleocene to the Quaternary using PyG plates and the Muller 2019 models. Due to the resolution of the age models that we have in MacroStrat, we kept this study to an epoch scale. So the points were rotated to their paleo positions on a base map that corresponds to the middle time point of each epoch through the Cenozoic. And then I calculated the sediment thicknesses that made the points on the map proportional to the thicknesses of all the sediment units in 0.5 degree latitudinal bins. And then I created paleobathymetry grids and backtracked the paleo water depth that the sediments were deposited at. So before I go into the results and the general trends that I pulled out of these data, I wanted to take you through how to interpret these maps. So the circular points are the biogenic components, which are the pink carbonate points, and the yellow are silicious, while the square black markers are clay. And as I said before, these points were grouped into 0.5-degree bins to improve their visibility on the plots. So basically, points that were within 0.25 degrees of each other fall into the same coordinate bin. And the size of these points correspond to the size of the thicknesses as indicated in the legend at the top. I've still got my marker, great. So if we look at this large pink point here off the South American coast, we can see that this point is carbonate point of around 200 meters in thickness, while this square point here is between sort of 1 to 10 meters in thickness. And so now I've introduced you to reading the map. I will take you through two of the case studies from this study situated in the North and South Pacific, because the other case study is the Equatorial Pacific. And when I say it's a huge amount to go through, it's basically a paper in itself. So let's get going. So the first case study is the Tasman Gateway in Australasia, which is the area highlighted here. And the Tasman Gateway is basically the deep ocean passage located between Australia and Antarctica, and it formed as the two continental plates drifted apart from each other, creating a major oceanic pathway that connects the Indian Ocean and the Pacific Ocean. So we can look at this region and how it evolved and how this altered the sedimentation accumulation through time. So we have here the same region, but with paleobathymetry maps. So now we have the added dimension of depth to aid our interpretation. So the lighter seafloor colours represent shallow regions, and then as we move to darker colours, the deeper the ocean is getting. So you can use this legend down here. And the grey areas of the seafloor that you can see predominantly more of as we go back in time are basically regions where the model couldn't resolve the seafloor bathymetry, either due to a lack of data or because of the seafloor being subducted. And as you can see here, the region around Australia remains very carbonate heavy for most of the record, with a bit more sporadic deposition of silicious and clay sediments as we move through time. And the opening of the Tasman Gateway is debated, but it is likely to have begun opening in the early to middle Eocene, which is the epoch before the Oligocene here. And then the onset of the Antarctic circumpolar current established in the late Eocene to early Oligocene as Australia drifted northwards. So as you can see here, the Antarctic circumpolar current is basically the current that circumnavigates around Antarctica and kind of isolates it. And so the early initiation of this current caused Antarctic sea ice to form and caused a major drop in temperatures of bottom waters and a significant drop in the CCD, which promoted rapid changes in biogenic sediment accumulation and increased the preservation of carbonate. And so if you cast your mind back to this figure, you'll remember that this is where the warm house then descends into the cool house, and we have this big drop here. So many studies suggest that there's a huge increase in diatomaceous ooze at the Antarctic circumpolar as the Antarctic circumpolar current initiates in the Oligocene, but this is not present here and agrees more closely with Bridget Wade's interpretations. And it suggests the deepening of the CCD means that carbonate remains the dominant lithology throughout this period of time. And then in the Miocene, we see this huge increase in abundance and thickness of sediments around the continent, which are dominantly carbonate still. And this is likely the result of the establishment of a number of different ocean currents throughout the Miocene. The Indonesian Gateway begins to restrict in the Miocene when Australia collided with Southeast Asia, leading to extensive carbonate shelves developing north of Australia. And then by around 10 million years ago, the Gateway was restricted enough to create a proto-warm pool in the Pacific and change thermohaline circulation pathways, including the beginning of the East Australian Current. So these changes led to increased plankton productivity and increased carbonate accumulation at the seafloor. And the prevalence of carbonate around Australia and New Zealand continues into the Pliocene and the Quaternary, predominantly in very shallow water depths, so less than 1,500 meters below sea level. And due to the rapid and orbitally paced glacial and interglacial sea level changes, especially during the Quaternary, the continental shelves were repeatedly flooded, which led to a large carbonate factory producing here, which is likely why we see the persistence of carbonate in these regions. As the Antarctic circumpolar current fully establishes towards the modern day, we would expect to see that there would be more siliceous material accumulating around here, which we don't. We see obviously small portions of it. But this is likely just due to a lack of sampling in the Southern Ocean and as well as the poor preservation of silica in general. And then the second case study is the Kuroshio current and the Tsushima warm current. The Kuroshio current is a powerful warm ocean current in the western North Pacific Ocean. And this current acts as a Pacific counterpart to the Atlantic's Gulf Stream. So it moves warm tropical water northward past Taiwan and the coast of Japan. And the Tsushima warm current is a branch of the Kuroshio current that brings warm and saline water into the Sea of Japan. So basically the Kuroshio current goes up like this, and then the Tsushima current flows up into here. So as you can see from these maps, the Oligocene has very thin and sporadic siliceous deposits in the region, but once we enter into the Miocene, we see a huge increase in both abundance and thickness of siliceous sediments, which is likely results from the evolution of both the path and intensity of the Kuroshio current and the inception of the Tsushima warm current. So the Tsushima warm current entered the Japan Sea between 12 and 11 million years ago as a result of the Indonesian Gateway restriction. And the initiation of these two currents also coincided with the reglaciation of the Antarctic ice sheet and global cooling, which caused this ocean current intensification and resulted in huge formations of biogenic silica. So many studies have identified both tropical and subtropical diatom species in these formations, confirming this increase in silica that's observed here. As we move to the Pliocene, it shows a very similar story to the Miocene, but with slightly less clay and more carbonate, as the climate cooled. And there was a tectonic transformation of the Sea of Japan at the time, which caused the Tsushima current to be transient, isolating the basin from warm currents. However, at 4 to 3 million years ago, the Central American Seaway closed and intensified the Kuroshio current again, bringing more warm waters into the basin, and this likely explains why we see more carbonate towards the present day. And in the Quaternary, we see a significant reduction in the thickness of sediments, which could be explained by Northern Hemisphere glaciation, which changed eustatic sea levels, making the Japan Sea fluctuate between oxic and anoxic conditions, impacting the biogeochemical cycles and subsequently the sediment-bearing organisms. So I could go on and on about these maps and what different currents cause what patterns, but I will leave it to you to read the paper when it comes out if you're interested in the nitty-gritty details. So now we know this research is not perfect, and so unsurprisingly, we have a decent section in this paper dedicated to bias. And when assessing sedimentological records and accumulation rates, it is essential to consider the biases that could potentially impact interpretations of the geological record. So I won't go into all of them today, but this figure quite aptly demonstrates a term that we have described as superposition bias, which is basically that we see this huge increase in sediment thickness as we move towards the present day. And within scientific ocean drilling, material is always accessed from the seafloor moving downwards into deeper sediments, thus always recovering material from youngest to oldest. And so this bias has a similar impact as the pull of the recent bias and is likely present within most summative analyses of scientific ocean drilling data. Further to that, ocean drilling data is inherently restricted by the feasibility of core recovery and expedition motivation. So some regions are heavily sampled, like the Equatorial Pacific and North Atlantic, while others are devoid of sampling, like the South Pacific and the Indian Ocean basin as a whole. And so the motivation of most scientific ocean drilling expeditions are typically trying to find carbonate, as that is what most workers are interested in. So we are likely to see more carbonate in records in comparison to silica, as well as it being harder to preserve in general. So essentially, there are a bunch of things to consider when we interpret this data going forward. Um, as you can see from this map on the right-hand side, which is in the upcoming publication, there is plenty of uncovered ground in these maps in all of the epochs. So it starts from the Paleocene to the Quaternary, and I have not touched on it. So there could be plenty of additional work looking at other case studies, such as the initiation of North Atlantic deep water, or the evolution of the Indian Ocean and the impact of uplift in the Himalayas. This would be especially effective if we could add higher resolution age models so that we could refine the maps to smaller time bins than just the epoch scale. But the best thing about EODP and the work coming out of it is that all of the code and workflows used in this study will be commented out as best as I can and freely shared online so that we adhere to the FAIR principles to make this work as reproducible and accessible as possible. So to conclude this seminar, I have managed to develop an improved framework for understanding Cenozoic sedimentation, and the data output seems to be reliable. The trends we are observing in Australasia and the Sea of Japan are reflected in the map outputs, and we have provided a framework that can also be built upon further. There are, of course, biases that we need to consider, but there's always plenty of room for super exciting work in the future. So again, I'd like to thank all of the wonderful people that have helped me through this project. It is definitely a team effort to get this volume of work done. And I'd also like to thank all of the funding organisations that have supported me, as well as Paleoperks again for hosting such a wonderful seminar series and for giving me the privilege of sharing my work. And finally, I'd like to thank everyone so much for listening to me yap for so long. I'll leave my email up on the slides and the various QR codes in case anyone wants to get in touch. But I am happy to take any questions that you might have.
Thank you for the great talk, Katie. That was super interesting. And thanks for the audience for all the applause. There is one question in the chat right now by Nourabis Hassan asking, I hope I pronounced it correctly. Hi, Katie. Is this gray colored polygon in the map representing sediments? Sorry, I am unable to get from the paleobathymetry scale. And I hope you can see it, but there is a picture included. I think this is the subducted or non-resolved parts.
Okay, sorry, I'm just going to get this up. Oh, sorry. Yeah, okay. So yeah, sorry, I didn't make it probably clear enough, but the grey areas on these maps are basically unresolved areas of data. So it's the model for paleobathymetry could not resolve those areas, and it's likely that that area has been subducted, or there's just not any available data for it. So the grey areas are basically areas to ignore. When I was reconstructing my points into their paleo positions, that was a lot of my basis for making sure that the model I selected was correct, because I wanted to make sure that as many of the points resolved within these areas that were feasible and displayed appropriately for this study. Yeah, I hope that answers that question. Amazing. Perfect. Thank you.
Okay, thank you. That's, yeah, Rabbi says it's clear. Yeah, so a reminder, you can send questions like more of this in the chat, or you can also send them to me, then they can be anonymous. So we have a few anonymous questions. Okay. I will just paste them in the chat right now so everyone can read it. So does it make a difference which plate model you use?
So yes, absolutely. It definitely does. And I did do a significant amount of model testing. That was a lot of my getting stuff together and making sure that it was the most appropriate model for this. A lot of these tectonic models are really focused at getting real deep time. So like beyond the Cenozoic into Mesozoic and beyond. So I was trying to concentrate on getting ones that were really good resolution for the Cenozoic in particular. And then I just did some model testing to make sure that like I say, all of the points were resolved in the appropriate areas. And when I say that, I mean they're obviously not in the middle of a continent and they're not in an area that has been subducted. So there was some trial and error trying out the different models, and I selected the Muller 2019 one. But if you were to do this again, people can take my code and very easily swap out the models. If a better model comes along, then they can absolutely be used in that way.
Yeah, that makes sense. Thank you for your answer, Katie. There is another question in the chat from Digne or Digne, not sure how to pronounce that, asking, might you comment a bit more on the post approximately 12 million years ago dates? Is that a data bias?
Right, yes. I think I can go. Sorry, let me see if I can go back to my bias screen. Right, so yeah, we we have basically termed this phenomenon, I'm going to call it, as the superposition bias. And essentially, what we're trying to say with this is, as due to the expedition themselves and the practicalities around ocean drilling, you are inherently going to be sampling more from the very top parts of the sediment cores. And so sometimes you'll hit basement and you won't be able to get any more depth that's possible. So basically, you're always going to get the upper layers of these cores, but you're not necessarily going to get data that spans sort of all the way back in this area, because if it's not available, it's literally not available. And so this might be why we see this increase, but we're not trying to say that it's impossible that this didn't happen. You know, there could be you know, different events that could have occurred, like increase in silicate weathering, or we have better preservation in this time. So there's like a bunch of different things that this could be attributed to. We were just trying to basically cover all of our bases and say this this could be a thing. And we've noticed it in other paleontological records aside from micropaleo. Like, it is, the pull of the recent bias is a well documented thing. So we've just kind of translated that same concept into here.
Thank you very much. There is a question that's kind of related to this this sediment thickness, asking, does compaction contribute to the recent thickness bias, and could this be corrected for, I assume, compaction in the cores that are analyzed?
Yeah, so that is a great question. Sediment compaction absolutely does play a part, and it is something we've considered. A lot of the modeling processes that I were doing in the preliminary steps that I didn't necessarily flesh out and explain in full detail, but they do account for sediment compaction and dynamic topography. So that is absolutely a possibility, but I have tried to correct for it. Whether it's sufficient, I don't 100% know, but yeah, it could definitely be an impacting factor for sure.
Thank you for clarifying. That's good to know. That's already corrected for a large margin. Let's see, there is another question from Julian Diaz asking, can this mapping framework be expanded to include the Caribbean and Eastern Tropical Pacific drill sites to help resolve the ongoing debate over the exact timing of the Isthmus of Panama closure?
Yeah, so absolutely. I think this is definitely, these sorts of questions are absolutely something that we want to get out of this data. In order to do that, we need better age models, because right now the resolution is pretty coarse. So this is why a lot of my maps are very like, oh, this could be because of this could be because of this. And even though there's basis behind that, it's not able to detect necessarily exact timings of things. Like, for the Isthmus of Panama closure. But if we get better age models and implement them into MacroStrat and the EODP framework, then we can absolutely start working towards answering these sorts of questions. And so this is just the start. This is just sort of like the first output of this project. And so we're really hoping that with future work on it, we can absolutely get to a point where that's possible.
That's awesome. Yeah, this seems like a great way to get more control on that. Okay, now Julian will take over the questions again.
Okay. So our next question is anonymous, and it is, why do we see a reduction of sedimentation in the Quaternary in the Sea of Japan?
Okay, yeah. So I I also have had these questions, and I have attributed it to Northern Hemisphere glaciation. And so the eustatic sea level rise and fall meant that the flows, these ocean currents were sort of more transient, especially in the Sea of Japan. And so that is my explanation as to why I think that could be a possibility, but I'd be more than happy and open to hear other people's interpretations of that.
Thank you. Going to put out a last call for questions. We have one more anonymous question. It says, amazing work. From having aggregated and integrated these data sets, would you have any suggestions for how to make macrostrat or the PBDB more accessible?
Oh goodness, that's a big question. Honestly, I think, oh, I'm going to be kicking myself because I'm sure my supervisor would have like a million things to say in answer to this question. But yeah, we're sorry, Andy's replied to me. What we're doing is trying to make MacroStrat and PBDB more accessible in this way. So we're trying to make the crossover between the taxonomic data and MacroStrat aligned so that we can get all of this data accessible. Inherently on their own, as they are, I think they do a great job in some aspects and maybe not so much in others. Um, it's a really tricky question for me to answer honestly. Yeah, I think a better framework. Actually, I do have a good question, good answer for this. I think having better frameworks and like coding workflows so that you can just download the data in a way that's easily manipulated and user friendly, it would be amazing. And so I remember, I mean, I haven't downloaded anything from the PBDB directly for a little while now, but I remember having so much trouble trying to import things on R and being like, oh my goodness, I don't know what I'm doing. I would love it if there was just like frameworks for this kind of stuff. So I'm guessing that's my answer. Better, like more accessible coding frameworks that are commented out and you can work out what people's packages are and things like that. I think that would be the best way. For me anyway. I'm sure there's plenty of other suggestions that people have.
Thank you for answering. I also work with the PBDB, and I agree. I think we should have
Great.
better workflow. But let's take a moment to thank Katie again. It was a wonderful talk. And we're going to put up slides now for next week's talk. Please fill out the weekly feedback form so that we can learn a bit about who attended this week. And next week, we will have Sanjukta Chakravorty from Stuttgart National History Museum in Germany, and that will be on August 25th, 1500 UTC, so same time. and that will be on vertebrate paleontology. So quite different.